the title here, not even, I will not even give it. It was string nets and universal RCFT correlators. So thank you for the opportunity to present this. If you have read the abstract, then you're expecting too much from this talk. I realized that I was a bit overconfident of how much I can do. Well, this is work with Christoph Schweigert and Yang, partly in a paper which appeared on the archive in December last year and partly unpublished. And I would like to tell you what string nets are, what RCFT correlators are, how you can use string nets to construct RCFT correlators. These string nets are colored, I will tell you what this means, by some category C. There's a bicategory FR of C, and it turns out you can also introduce string nets which are colored by that bicategory, which allows you to understand some additional aspects of correlators, and that leads to some structure we have called universal correlators. And I hope that I will have enough time to explain at least roughly what these are. And if there is time left, I will make a few comments on how these universal correlators fit into a setting which uses double categories. So let me start with one. Who of you is familiar with string nets and the string net construction? Not so many. So I will go into some details. The construction originally goes back to the condensed matter physics literature by Levin-Wen in 2004, but the way I will describe it is due to Sasha Kirillov from 2011. And in Kirillov's approach, the main result is that these string nets can provide a modular functor, and this modular functor is isomorphic to the Turei-Viro modular functor, and even that extends to a 1, 2, 3 extended topological field theory. And I will not say much about that part, but I want to tell what the basic construction is. First of all, there is an input category C. This is a spherical fusion category. Spherical fusion category means it's a tensor category in the sense of what Dimitri told you yesterday. And in addition, you have dualities, left and right dualities, in such a way that the double dual is monoidally isomorphic to the identity, and also in a very nice way that's covered by this qualification spherical. And in addition, that's covered by the term fusion, the category semi-simple. Everything in this part 1 here assumes very explicitly that the category is semi-simple. When we talk about RCFT, rational conformal field theory, we are also in a semi-simple context. But parts of what I will do here, parts of the tools one is using, actually extend to certain non-semi-simple settings. What do we need for our construction? We deal with surfaces, which we call sigma. This is a surface. Possibly with boundary, which is compact, smooth, and oriented. No, it's not braided. Actually, in the application in 3, it will be braided, but for the construction here, it's not braided, but we have heard yesterday from Dimitri that to a category of this type, there's naturally associated the Drinfeld center, which is braided, and that will play also an important role. Then we need graphs, gamma on, and by a graph, again, I have to require some properties. It should be finite, should be oriented, and when I talk about graphs, I think of them as embedded in the surface. So I will draw a graph directly into my surface. And it should be finite, so finitely many vertices and edges. And in addition, if there is a part of the graph which is on the boundary of the surface, then it's a one-valent vertex. And then there is a coloring of such graphs by the category C. By this, I mean that to the edges of the graph, I assign objects of C, and to the vertices, I assign morphisms. And more precisely, and there is already a technical point here, which I will essentially suppress, is that if you have, well, I said oriented graph, so I should better orient these. They should learn to count. Orient the edges. Then, if the edges which are incident to the vertex are labeled in this way, then phi would be an element of the morphism space in C. I will suppress this from, say, 1 to x1 tensor x2 dual tensor x3. And you see, when I say this, I have chosen a starting point here. There is a natural cyclic order around the vertex, and I have chosen one particular linear order. This is an auxiliary information. You have to make sure that in everything you will do at the end, nothing depends on this, but it doesn't. And well, you can actually formulate things in such a way that this is not a morphism in a morphism space, but it's a limit of something else which is uniquely defined. But, so we have these colorings, and let me see, in, out, out, out. Thank you. I actually think my real convention is the other way around. But no, we just take some morphism. Arbitrary morphisms, they do not need to be, well, since C is a fusion category, it's semi-simple, so you can express everything in terms of simple objects and in terms of morphisms from x1 tensor x2 to x3, but that only makes formulas more complicated, and it doesn't really help you for conceptual questions. There is also an obvious notion of isomorphism of colorings, namely families of isomorphisms of objects such that the two colorings are related by acting with those isomorphisms on the objects, on the edges, and in a compatible way on the morphisms. And Then an important further notion is a boundary value of the graph gamma. By this, one simply means a finite collection of disjoint points on the boundary. So maybe, so not of gamma, of sigma. So assume, well, maybe I should add some other component of the boundary somewhere. So a finite collection of points, disjoint points, say some here, and to each of those points, we associate an object of C. And for this, we do not need a graph. So maybe I remove this part of the graph for the moment. So there are objects of C. So this, well, let me just write collection of colored points. On D sigma. And now we define a vector space, which, well, we need some name for it. Let me call it G of sigma. Sigma, some surface, B, some boundary value for the surface. So maybe the B here by the following prescription. This is the vector space really generated by all graphs in the sense of embedding graphs on sigma such that sigma such that gamma restricted to the boundary gives us the boundary value. Well, it gives us the information that we have by the graph on the boundary. I don't write this out, so that simply means if this graph is there, then to this point, one of the part of the information that we have in the boundary value of sigma, we have to associate the object that we have here. To be precise, in this case, here we would take x1 dual with the same convention as here for an outgoing edge, and for an ingoing edge, we would take x1. Now, this space is, of course, huge, freely generated by arbitrary graphs, finite graphs, and so on. So this is of not much use, but now the interesting thing is that you I don't require my surfaces to be connected. So also the graphs do not have to be connected. But when I draw something, I think it will always be connected. But you, everything you do is working in such a way that when you deal with disjoint unions on the linear side, there will be tensor products. Yes, arbitrary. I will, when I say graph from now on, it will always be an embedded colored graph. Now we want to get from this some nice space by dividing out some relations, and for that we first consider the case that sigma is a disk. So we we have a disk, and then there will be some embedded graph. Let me draw a simple one here. And now, via the graphical calculus for these monoidal categories, it's important they are spherical. So there is a spherical graphical calculus where you have some cyclic property around the morphisms. You can relate. You can think of this graph gamma as representing a morphism in a morphism space of C. So this you would can map to some phi in a corresponding Hom space analogous to the one over there. And now you say that, by this you get a canonical surjection from the space here for the disk to with chosen boundary value to this morphism space, and then you just divide out the kernel of that space. So, sorry, then. And you can see that in fact this space here is canonically isomorphic to this huge space for any boundary value b divided by the kernel of this map. And in particular, this means that it's finite dimensional, which is well, something you might not expect to achieve easily, but that is indeed a direct consequence here. And now you extend this idea to general surfaces by saying that for general sigma, you say that a graph is a null graph with respect to some embedded disk D, where the disk has to be chosen in a way such that it doesn't interfere too much with the graph, so it should intersect transversely and so on. And then you say that let me write gamma tilde. This is a linear combination of graphs. On sigma such that that it's mapped to 0 by this map. And I should give this a name like that. It's Kirillov's notation, I think. And now, once we have this notion, we can define the null space n of sigma and b, so fixed sigma, fixed b. This is just the subspace of this big vector space spanned by all null graphs. Remember, null graph means a linear combination. Still, you call it a null graph. Null graphs on D for any embedded disk. So this is again a huge space, and then finally you get a finite dimensional vector space by defining the string net space, the Sn for string net with an index C, which I will often forget, for sigma and B is just the quotient of G of sigma D by N of sigma D. And this is finite dimensional. And this is not what I want to write. I put a little 0 here, and sometimes one calls this the bare string net space. And what is why I have this qualification, we will see in a minute. Now, since you get to this space by using by implementing this graphical calculus for the category C, actually you can easily calculate with this, because when you can manipulate string nets by using the rules of the graphic locally on the surface using the rules of the graphical calculus. And I say manipulating string nets. In principle, by string net, one means an element in the space which comes from one of the generators of the big space, but one also uses it sometimes for linear combinations, and also one uses the term not only for these classes, but also for representing graphs. So I will often abuse terminology by calling a graph a string net. What is meant is always it's a string, that's a string net for which a graph is a representative. Well, locally, yes, yeah. So that's a possible way to think of it, I would say. Yes. Now, also notice that diffeomorphisms of the surface naturally act on graphs, and that descends to this space, or this space carries an action of the mapping class group of sigma. Well, a mapping class group, you fix boundary values, but I don't want to go into details about that. Also, it's clear that you can, when you sew surfaces, you can which have such embedded graphs. If they fit together, you can sew surfaces with graphs. So there's a sewing of string nets, and when you do this in details, there are some technical complications, but it's not really complicated. What, on the other hand, is an important additional aspect, which is not accounted for yet, is this 0 here. The point is we want to associate actually categories, well, to make boundary values into categories, and for that, maybe I will start here. There is something called a bare cylinder category, CIL O for a one manifold, S, where the objects are boundary values. Well, I have introduced boundary values for the boundary of a surface, but the same prescription you can do for any one manifold. And then the morphism space. From S, the morphisms are just string nets, the space string net space on S cross the interval I. So if I have S here and another copy of S and the cylinder over it, there might be some, well, boundary value means I choose some isolated points, and a string net is then a graph, well, represented by a graph where anything can happen here, well, any morphisms like that. This form, also this form, and where the boundary for values for these graphs are given by the boundary values B and B prime. Well, for one of them you have to take duals, so we have to introduce a notion of duality for boundary values. That's actually, I tried to suppress this. We will allow, at least for now, we will allow for manifolds with boundaries. So they are they are finite disjoint unions of circles and intervals. And this is called sometimes called a cylinder category, or also bare cylinder category, and analogously this is called a bare string net space. And now the problem with these categories is that they are not nice. For example, they are not abelian, but one can show. Kirillov has shown that if you now define CIL of S to be the Karubin envelope of this category, and this is an abelian category. So Karubin envelope means idempotent completion. So the objects here are pairs of objects that you have here, and idempotent morphisms in the, sorry? Pairs, objects in the Karubin envelope are pairs consisting of an object here and wait, these are objects. Yeah, I was pointing wrongly. Objects here are pairs consisting of an object here and an idempotent. Well, a morphism which squares to itself. If you compose an endomorphism which P, such that P composed with P is equal to P. Well, there can be such, you don't add anything. For any such idempotent you have in your category, you look at such a pair, and then it's an object in the new category. Now there are some important results, other results, namely the cylinder category, and now I allow for intervals. This is canonically equivalent to C. Well, how do you do that? If you have an interval, along the interval you have points which are labeled by objects, so you just tensor them together. Whereas for, well, on objects, and then you know what to do on morphisms. And for S1, and this is quite a bit more elaborate, you get actually an equivalence to the Drinfeld center of C, where again you take such tensor products in some linear order which comes from the given cyclic order, and again you have to see that things do not depend on that, and then you apply the functor L, where L is left adjoint L to the forgetful functor from the Drinfeld center to C. So remember, objects in the Drinfeld center are pairs consisting of objects in C and half braidings, and you just forget about the half braiding. I will not get very far. But at least we are now done with, almost done with string nets. Once we have done this this correlification here, we can now define the full string net space or corrubified string net space. Sn B of sigma and B, where now B corresponds to an object, well, to object xb and some idempotence. Then you define this as the image of an idempotent on the bare string net space, which comes from the idempotence you have on the in the cylinder categories associated to the boundary of your surface. And these are the vector spaces that play a role in Kirilov's construction and which play a role in part 2 and no, part 3 of what I want to say. So in principle, this is not the end of part 1 yet. There is an important, well, one of the main results of Kirillov is that this construction actually provides you with a modular functor and actually in a modular functor in the case that you only allow for closed one manifolds as for which you have these cylinder categories, but it's not so hard to show that you can extend this also to the case where you have boundaries, and the main point is that if you have, you will anyhow deal with surfaces which have boundaries, but not more complicated. So boundaries for a surface will always be geometrically circles. But on these circles, you can have intervals to which you attach your cylinder categories. And to these, for each individual interval, the cylinder category is just C. But then what you do is you take the objects you get here, tensor them again, and apply again L, and then you are back in a setting where you can do everything that that Kirillov has been doing. So, and then I should, in order to make this result precise, I should define precisely what the modular functor is. That would take the rest of my time. So it's in the setting that we are using. It's a two-functor from a category of bordisms, which are called open-closed bordisms, because we allow for these intervals, and are oriented to, which is naturally a bicategory to the bicategory of profunctors, which is the bicategory which has as objects finite k-linear categories. K is an algebraically closed field, which is part of the spherical fusion category, and profunctors. That means a profunctor from a category A1 to a category A2 is defined as a functor from A1 opposite the linear product with A2 to vector spaces. And two morphisms are natural transformations of these, and the tensor product for profunctors is using a kind of convolution product. Technically, this uses coends. And now, part two. This will be as short as I can possibly do it. So we have some rational conformal field theory. The input is modular fusion category, which again I call C because it will be the same C as here. So for part one, C was just a spherical fusion category. Now we assume that it's in addition braided, and the braiding is is maximally non-degenerate. That's what is called a modular fusion category. We can actually, for some of the calculations, dispense of the requirement of semi-simplicity, but then one needs certain finiteness conditions, and there are, for finite tensor categories, there's also a notion of modular finite tensor category. And therefore, some years ago, one would have said modular tensor category, but in order to stress semi-simplicity, I write fusion here. Then we this is one input, and other input are worldsheets. And what is a worldsheet? I only say it in words for now, and it's not yet complete. It's a surface together with which has a conformal structure, and in addition, there can be what one in conformal field theory calls field insertions, meaning which can be realized as associating objects in the Drinfeld center of C to embedded circles. So actually you cut out some small disks, and the resulting boundary circle to that you associate an object in the Drinfeld center. And if there is already a boundary, sometimes called physical boundary, to distinguish it from these boundaries coming from field extensions, on that boundary circle you can have intervals in the same way as here. And to that now for a worldsheet, let me call it S. For a worldsheet, there is always an ambient or underlying surface in the sense used before sigma. You just forget all the information that is not needed. From what I said, essentially you don't have to forget anything except the labeling, but there will be more to worldsheets in a minute. And then for this surface here, the modular functor that you have from part 1, associates to you vector spaces, and these are called, in conformal field theory and also otherwise, they are often called conformal blocks. Now, actually, there is a description of modular functors in this setting, which does not guarantee that it's the same thing as what we have been talking about, but Kirillov has shown that the modular functor constructed this way is actually isomorphic to the modular functor obtained by the Turaev-Vira construction for C. Now, the modular functor corresponding by that modular functor is isomorphic to the modular functor obtained for the Rezhikhin-Turaev construction for the Drinfeld center of C, and it's conjectured and generally believed that that modular functor is the relevant for one relevant for conformal field theory, and I will assume that. There are people who say it's proven, but well, as I said, part of what we are doing extends beyond rational. In that case, we have to take still, a modular finite tensor category. For example, these coends and the linear products that one is using, they still make sense. These are, or are expected at least, to be the relevant categories for certain logarithmic conformal field theories. Essentially, well, those which behave like the 1, p models, but then there are those which behave like p, q models, which don't have ordinary dualities, and those cannot be covered here. Then one needs to go to do quite a bit more, and it's not that's not understood at all yet, I would say. Now, what is a correlator? Correlator is a specific element in the space of conformal blocks, correlator for S, and let me call this maybe the surface sigma S, specific element in this space of the relevant space I have to add something, but let me finish the sentence. A specific element in the relevant space, such that, first of all, it's invariant under the mapping class group of S, and it's compatible with sewing. I should add here a hat. Indeed, what you the relevant space of conformal blocks is let me see. The worldsheet in general need not be oriented, so you have to be careful with here. You actually have to look at the double cover of the surface, and that well, maybe I don't go into that. So compatible with sewing is not so hard to understand. We can sew worldsheets, just we sew surfaces, and so there are sewing isomorphisms between the corresponding spaces of conformal blocks, and you just have to you require that starting with a particular element in one space, applying that specific isomorphism, you get the distinguished element in the other space. A mapping class group here means, well, it's a subgroup of the mapping class group of the surface here. And for that, it's relevant that in addition to what I have said so far about worldsheets is that they contain what are called defect lines or topological defect lines. These are, maybe I should draw again such some worldsheet. So we maybe some other. We have in the surface one-dimensional submanifolds, and they are now they are very simple, but they have to be labeled, again to be labeled, and they are labeled as follows. The two cells that we get here, any two cell is labeled by a simple, special, symmetric Frobenius algebra. Internal to C. So Frobenius algebra is an algebra in co-algebra, such that the co-multiplication is a morphism of bimodules. Symmetric means that, well, a certain, well, in the graphical calculus, if you take the product, co-unit, and the duality, that this morphism is the same as this morphism, where you have left and right duals here. So this is up to a pivotal structure, and special is a certain non-degeneracy condition. Simple means simple as a bimodule over itself, and so you have labels, say A1 on one side, A2 on the other side, and then the labels for the defect lines are bimodules over these algebras. And then you can have, of course, you can have also junctions between those. You can have insertions, field insertions, which now, maybe I do a more complicated one here. So you have some ingoing and outgoing defect lines, and again you have to associate to this an object in the Drinfeld center of your category, for which there is a simple prescription. And now in this situation, the mapping class group for your surface is a subgroup of the mapping, for your worldsheet is a subgroup of the mapping class group of the underlying surface, which leaves these defect lines invariant. So it's typically much smaller. And now, maybe that's enough about part 2. Part 3 is now string net correlators, meaning we use string nets to obtain specific elements in our string net spaces and then check that they satisfy these requirements. So they give us correlators of conformal field theory, a consistent system of correlators for arbitrary worldsheets. And this consists of 2 parts. First of all, we interpret the worldsheet as roughly a surface with embedded graph. So we colored graph, remember? So graphs in surfaces are colored by objects. So we forget here about the algebra actions, and we forget about the algebra here. So these are actually give us string nets, elements in relevant string net spaces, and then on each 2-cell we insert what is called full Frobenius graph. So what is that? Well, a Frobenius graph is just a finite graph again, which has only 1-valent and 3-valent vertices. Each, so we are given such a Frobenius algebra A. Each of the edges is labeled by A. It should be an oriented graph, but because of the properties of A, there is A is as self-dual as possible. That's one way to say what a Frobenius algebra is. So I don't have to indicate that. And then this is in a 2-cell, which is bounded somewhere by defect lines. And then if you have points at which the graph touches this boundary, the vertex has to be just one edge attached, and to these 3 to the vertices with 3 edges, we assign the product or co-product depending on choice orientations. If we have a vertex like that, this would be the unit or co-unit of the Frobenius algebra, and on the boundary we associate representation morphisms. So this is a Frobenius graph. There are equivalence relations because we can use, in particular, simple means that we can make such replacements. And now a full Frobenius graph means that it's a graph such that if we add any additional vertices and edges via the relations that we have, we can reduce it to the original graph. And that means that in the end, what we have is a string net roughly looking like that. and then in each of these two cells, we have corresponding such Frobenius graphs. If we are in the simplest possible situation, namely that we have only one phase of our theory, so we have just one such algebra and take the simplest one, namely the tensor unit, then essentially these lines are invisible, and there are no defect lines. Then the correlator is given by the empty string net, and very clearly the empty string net is invariant on the mapping class group. If you have the general situation, then you have to use the fact that when you apply a mapping class or a diffeomorphism in general to one of these full Frobenius graphs, you get another full Frobenius graph, and then you show that the correlator you get for any two full Frobenius graphs in a given two-cell that they are actually identical. Okay, my time is over. Maybe I can make one short statement about part 4. It's rather obvious from the picture here that, and also in view of known results from conformal field theory, that it somehow would make sense to think of these two cells as actually colored by this algebra. You can think of getting these full Frobenius algebras by punching holes in your two-cell and taking a deformation retract. And accordingly, it's not so surprising that you can formulate a variant of the string net construction where instead of graphs, you take two graphs, meaning graphs of the same type, but in addition, you label your two cells, and they are now not labeled by C, but rather by the bicategory FR of C, where the objects are these Frobenius algebras, one morphisms are bimodules, and two morphisms are bimodule natural transform bimodule morphisms, and the tensor product is the one for bimodules. It turns out that you can do that, and it turns out that this has an additional benefit, namely, when you look at the situation here, it still happens that there are different world sheets, different according to the precise definitions that one has, which actually have the same correlator functorially, so for arbitrary choices of assignments of labels. So for example, if you have a situation where you have two parallel defect lines labeled by bimodule B, and which is invertible, and this one by the invertible one, you will get the same correlator when you replace this situation by this one. But these are different world sheets. However, in this Frobenius of C colored version of the string net construction, you automatically have implemented relations such that you get the same string net spaces for these two situations, and you can show that actually you get the same correlators precisely, but because these are in the same spaces by construction, actually you have already implemented in your construction an identification of world sheets. And if you do this in detail, then you can show that there is a certain map from the string net spaces you get for this Frobenius of C-colored string nets to those that I described in part 1, in such a way that this map intertwines the action of the mapping class groups on those spaces. And if you look at further properties of that map, it's rather natural to call those maps universal correlators. And still one more sentence. Part 5 says that the fact that this works out has a natural explanation in terms of double categories. Thank you.